In a world where air superiority defines the balance of power, a single question lingers in strategic circles. Could China's J-35 stealth fighter ever hypothetically match, or even down, the American F-35 Lightning II? The answer remains uncertain, yet the mere possibility reveals how far China's aerospace ambitions have advanced. The emergence of the J-35, a fifth-generation stealth aircraft designed for both the Air Force and the Navy, signals Beijing's determination to close the technological gap with the West and reshape its role in the skies above the Indo-Pacific. At the dawn of the 21st century, the evolution of air combat entered a new phase. Dogfights were no longer decided by who could climb faster or turn tighter, but by who could remain unseen, detect first, and strike from afar. The fifth-generation era began, defined by stealth, advanced sensors, and digital integration. The United States led this revolution with the F-22 Raptor and the F-35 Lightning II, two aircraft that fused speed, stealth, and networked warfare into one seamless platform. These jets became benchmarks that every other power aspired to meet, but few could approach. Russia introduced its Su-57 Felon, while China embarked on an accelerated campaign to produce fighters that could rival American dominance. The first result was the Chengdu J-20 Mighty Dragon, which entered service in 2017 as China's first operational stealth fighter. However, while formidable, the J-20's large frame and emphasis on range made it closer in spirit to the F-22 than to the more compact and versatile F-35. China needed something else, a carrier-capable stealth jet that could provide flexibility for both land and sea operations. Thus, under the Aviation Industry Corporation of China, AVIC, and Shenyang Aircraft Corporation, work quietly began on a twin-engine stealth design known as the J-35 or FC-31. Development stretched over a decade, with numerous wind tunnel studies, stealth geometry refinements, and materials tests, culminating in its public appearance at the Zhuhai Air Show in 2024. The event was more than a debut, it was a declaration. With the J-35 now capable of takeoff and landing trials on China's newest aircraft carriers, the nation demonstrated it could potentially field not one, but two stealth fighters, the J-20 for air dominance and the J-35 for multi-role operations. If mass production follows, China would hypothetically become the second country after the United States to operate dual fifth-generation fighters across its air and naval branches. A senior commentator on China's state broadcaster hinted that the J-35 could soon enter regular production for carrier-based squadrons, enhancing the People's Liberation Army Navy's power projection in the Pacific. In appearance, the J-35 carries subtle echoes of the F-35's aerodynamic philosophy. Its blended wing-body frame, twin engines, and canted tail fins minimize radar reflection, while its smooth surfaces and sharply angled inlets indicate a focus on stealth optimization. Many Western analysts argue the resemblance is not coincidental, suggesting that some design inspiration may have originated from cyber theft or industrial observation. Beijing, however, maintains that its engineers independently achieved the design through computational fluid dynamics and trial-based refinement. Regardless of origin, the result is a sleek, radar-resistant form optimized for low observability. The J-35 reportedly flies at altitudes approaching 20,000 meters, with a top speed near Mach 2, roughly 2,470 kilometers per hour. Its internal weapon bays preserve stealth while allowing it to carry a balanced load of precision missiles and bombs. Beneath the surface, radar-absorbent coatings cover most of the airframe, and the exhaust nozzles are shrouded to reduce infrared visibility. Together, these details allow the aircraft to evade radar systems and infrared search and track sensors, at least in theory. Yet, as most analysts note, stealth on paper and stealth in real combat are different realities, and many aspects of the J-35's true radar signature remain hypothetical. In terms of weaponry, China's engineers have equipped the J-35 with some of the country's most advanced systems. The PL-15, a long-range air-to-air missile measuring nearly 4 meters, can reportedly engage targets more than 200 kilometers away using an active AESA radar seeker and anti-jamming features. It travels at speeds approaching Mach 4 and is considered one of the most formidable missiles in its class. Paired with it is the PL-10, a short-range infrared-guided missile optimized for dogfighting, capable of Mach 2.5 and highly agile. Both weapons allow the J-35 to engage targets across multiple ranges, from long-distance interceptions to close-quarter duels. For surface attack missions, the aircraft is believed to carry the KD-20 cruise missile with a range of roughly 2,000 kilometers. The missile can fly at low altitudes, hugging terrain to avoid radar detection, and uses a hybrid guidance system of GPS and terrain matching to ensure accuracy within a few meters. The J-35 can also deploy LS-6 laser-guided bombs, smart munitions designed to strike fortified structures, radars, or warships. These payload options, weighing up to 8,000 kilograms, make the fighter adaptable to both air superiority and precision strike roles, depending on mission requirements. At the sensory level, the J-35 is built around an active electronically scanned array, AESA radar, China's most advanced to date, capable of detecting multiple targets simultaneously and guiding several weapons in flight. It theoretically enables the aircraft to operate as both a hunter and a node within a broader network. The system integrates with electronic warfare modules, infrared search and track sensors, and encrypted data links that allow it to share targeting information with other jets, ships, or command posts in real time. If proven effective, this kind of digital cooperation would represent a major leap for Chinese aviation, moving it closer to the network-centric warfare model long perfected by Western forces. One persistent challenge, however, lies in propulsion. Early J-35 prototypes used Russian RD-93 engines, dependable but dated and far from stealthy. Their exhaust emitted visible smoke, and their heat signature made them vulnerable to detection. To eliminate this weakness, China began developing indigenous replacements such as the WS-13, WS-19, and WS-21, aiming for more thrust and cleaner performance. The WS-21 in particular is said to deliver over 32,000 pounds of thrust per engine, potentially giving the J-35 a high thrust-to-weight ratio. Still, the project faces technical hurdles. Engine reliability and smoke reduction remain works in progress, and until these issues are solved, the J-35's full stealth potential remains hypothetical. The materials and structure also play a major role. Engineers used aluminium-lithium alloys and carbon fiber composites to keep the airframe light and strong. The triangular wing design generates more lift and agility, crucial for dogfights and carrier landings. Coupled with a fly-by-wire control system, the aircraft can theoretically perform complex aerial maneuvers similar to Western designs. Yet, without extensive combat testing, those capabilities exist mostly in simulation. Perhaps the most interesting feature of all lies not in its engines or missiles, but in its integration philosophy. The J-35 is built to share information instantly across platforms, other aircraft, naval ships, and ground stations. Through high-speed data links, it can help create a real-time tactical picture for commanders, turning separate units into a unified digital swarm. In theory, that connectivity could compensate for limitations in radar or stealth, emphasizing teamwork over individual performance. Ultimately, the J-35 embodies China's determination to achieve aerospace self-reliance. Every sensor, composite layer, and engine turbine represents another step on from foreign dependency. Whether this aircraft can truly match the F-35 remains a matter of speculation, but its existence alone proves a point. The gap between China and the West is narrowing, at least on paper. In conclusion, the J-35's story is as much about symbolism as it is about technology. It represents a nation striving to transform ambition into capability, imitation into innovation. For now, most of its features remain hypothetical, its stealth untested in battle, its engines still evolving, its sensors awaiting full integration. Yet its emergence marks a new chapter in the competition for the skies, one where the boundaries between imitation, innovation, and inspiration are increasingly blurred. The real test will not come from air shows or propaganda reels, but from time, data, and the unforgiving lessons of real-world operations. And that, perhaps, is where the J-35's greatest challenge still lies. When comparing two of the world's most advanced fighter aircraft, the line between fact and speculation becomes thin. Much of what is known about the Chinese J-35 remains hypothetical, while the American F-35 Lightning II has already accumulated thousands of operational hours across multiple combat zones. Yet the contrast between them reveals not just two machines, but two philosophies of warfare, one honed by decades of combat experience, the other built through accelerated ambition and imitation. Hypothetically, the J-35 holds some clear advantages in raw performance. Its dual-engine configuration, for instance, offers greater thrust, redundancy, and higher service ceilings compared to the F-35's single Pratt & Whitney F-135 engine. Estimates suggest the J-35 can reach Mach 2, while the F-35's top speed caps at Mach 1.6. At high altitude, the Chinese jet could theoretically climb several thousand meters higher, around 20,000 compared to the Lightning's 15,000. On paper, this means faster intercepts, more energy for maneuvers, and a better ability to escape low-level air defenses. Yet the numbers only tell part of the story. True air dominance depends not on speed alone, but on how information, stealth, and survivability interact under pressure. The J-35's potential reach in long-range combat comes largely from its PL-15 missile, whose range of roughly 200 kilometers exceeds that of the F-35's current AIM-120 AMRAAMs, which operate effectively around 110 kilometers. In a hypothetical engagement, this might allow a J-35 to strike first, assuming it can detect, identify, and maintain lock on its opponent. But those assumptions lean heavily on sensor quality and networking capability, areas where the F-35 still dominates. The Lightning II's distributed aperture system, advanced infrared targeting, and multiband radar give its pilot a seamless 360-degree picture of the battle space. Combined with data from nearby F-22s, AWACS, or drones, the F-35 pilot often sees the fight long before the enemy does. This level of situational awareness is the product of years of integration work, hardware and software blending into a digital nervous system. It's what allows the F-35 to fight not as a single aircraft, but as part of an ecosystem. Hypothetically, even if the J-35 could match its speed or range, its ability to operate as a node within a fully networked environment remains uncertain. China's data link systems have improved rapidly, but interoperability across air, sea, and space domains is still developing. While the J-35 can share tactical data among friendly units, the maturity of that system compared to the F-35's Link 16 and Multifunction Advanced Data Link (MADL) remains unverified. Maintenance and operational reliability mark another critical difference. The F-35 program, despite early setbacks and cost overruns, now benefits from over a decade of field data and upgrades across Allied air forces. Its predictive maintenance software monitors each component's health, reducing downtime and ensuring consistent mission readiness. In contrast, the J-35 is still in its testing phase. Hypothetically, Chinese engineers may face the same learning curve the U.S. experienced during the F-35's early years: software integration bugs, supply chain vulnerabilities, and high maintenance demands for stealth coatings. Stealth aircraft are notoriously complex to maintain. Even a small imperfection in the radar-absorbent surface can compromise its invisibility. Economically, China holds an advantage in production cost. By relying entirely on domestic suppliers and state-controlled industries, the J-35 could theoretically be built for a fraction of the F-35's price tag, which exceeds USD 80 million per jet for most export variants. Estimates suggest the Chinese fighter might cost under half that figure, allowing for mass production without dependence on foreign partners. This would enable Beijing to field more aircraft quickly, a quantity-driven strategy that contrasts with America's quality-centric doctrine. However, cost efficiency can sometimes mask hidden trade-offs, such as limited software sophistication, lower mission system reliability, or less refined pilot training infrastructure. In maneuverability, the J-35's twin engines might provide a slight edge in thrust vectoring potential, assuming future models integrate nozzle control technology. Its triangular wings and fly-by-wire system suggest strong aerodynamic agility. Yet the F-35's real power lies in its ability to manage that agility through sensor fusion and automatic flight controls. The pilot's helmet, a 21st-century marvel, merges all sensor data into a single visual feed, even allowing the pilot to see through the aircraft's fuselage. Hypothetically, this gives the F-35 pilot a faster decision loop, translating information dominance into tactical advantage. In modern air warfare, the one who reacts first usually wins, regardless of who flies faster. The F-35's greatest strength may be its versatility, available in 3 variants: the F-35A for conventional takeoff, the F-35B for short takeoff and vertical landing, and the F-35C for carrier operations. It can adapt to nearly any environment. It supports ground attack, reconnaissance, and electronic warfare missions, all while maintaining stealth. The J-35, though designed for carrier use, has yet to demonstrate similar flexibility. Its engines and landing gear have only recently completed trials aboard China's carriers, and the challenges of maintaining stealth integrity in harsh sea conditions remain significant. The F-35's naval variant, by contrast, has operated for years from U.S. and Allied decks worldwide. When it comes to experience, the gap widens further. The F-35 has been tested in real combat, from Middle Eastern theaters to NATO exercises in Europe and the Pacific. Every sortie provides data that feeds back into upgrades, refining software, sensors, and weapons integration. The J-35 has yet to face that crucible. Until it does, many of its capabilities will remain theoretical, its performance verified only by controlled trials and public demonstrations. History suggests that combat experience, more than engineering, defines a fighter's evolution. And for now, the F-35 has that experience in abundance. Still, it would be a mistake to dismiss the J-35 outright. The aircraft represents the culmination of 2 decades of relentless catch-up. Even if its stealth and sensor systems are not yet equal to those of the F-35, its appearance signals that China can now produce advanced fighters at scale, narrowing the technological gap that once seemed insurmountable. In a hypothetical conflict scenario, sheer numbers, combined with long-range weapons like the PL-15 and coordinated drone support, could create challenges for even the most sophisticated Western forces. The J-35's ability to launch from carriers also extends Beijing's air reach across the South China Sea and beyond, allowing for greater presence operations, though such deployments remain theoretical for now. One area where the two fighters diverge most sharply is doctrine. The F-35 embodies Western emphasis on precision, interoperability, and networked command. Its purpose is not merely to dominate dogfights, but to function as an airborne command node that supports other aircraft and ground forces. The J-35, in contrast, fits China's more centralized doctrine, an emphasis on protecting regional interests and projecting limited force beyond its borders. Hypothetically, the J-35 may not need to surpass the F-35 globally. It only needs to perform effectively within China's regional strategy, particularly around the Taiwan Strait and South China Sea. In that narrower context, even a slightly less capable platform could have major strategic impact. There are, however, areas where the F-35's dominance remains clear. Its stealth coatings have undergone years of refinement, proven to perform under different climates and carrier conditions. Its logistics network spans dozens of partner nations, creating a shared pool of parts, maintenance facilities, and software updates that no rival currently matches. Every upgrade cycle, from Block 3F to Block 4 and beyond, adds new weapons and computing power. The J-35's modular architecture may allow similar improvements in the future, but those efforts are only beginning. From a geopolitical perspective, the J-35's emergence raises questions less about immediate parity and more about long-term balance. If China can mass-produce stealth aircraft that are good enough, it could change the calculus of deterrence. Quantity, cost control, and domestic autonomy might allow Beijing to sustain large fleets, while America continues to invest in fewer but more expensive systems. This asymmetry reflects a broader strategic divide. The West prioritizes technological superiority, while China pursues sufficiency through scale. Both paths can redefine air power in different ways. Ultimately, the competition between the J-35 and F-35 may not be decided by dogfights in the sky, but by which nation adapts faster to the digital age of warfare. Artificial intelligence, network integration, and real-time data sharing will shape the next decade far more than aerodynamic margins. In that context, the J-35's development shows that China is learning quickly, integrating lessons from past gaps and steadily building toward self-sufficiency. But to truly rival the F-35's proven ecosystem of technology, training, and allied integration would require years, perhaps decades, of continued refinement. Hypothetically, if both aircraft were to meet under equal conditions, much would depend on situational context, radar environment, pilot skill, supporting assets, and electronic countermeasures. The F-35's advantage in data fusion and experience might tilt the outcome, but the J-35's longer missile reach and two-engine design could offset some of that edge. It's a contest less of raw power and more of systems thinking, a chess match where visibility, timing, and coordination matter more than speed or firepower. In the end, whether the J-35 can truly down an F-35 is less a technical question and more a strategic one. The aircraft symbolizes China's ambition to rewrite its position in the aerospace hierarchy. For now, that ambition remains mostly hypothetical, a bold promise built on prototypes, projections, and political theater. But history has shown that ambition, when backed by persistence, can reshape the future of warfare. For the United States and its allies, the emergence of the J-35 is both a challenge and a reminder. Technological dominance is never permanent. For China, it is a statement of intent, proof that the race for the skies is far from over. And for the rest of the world watching from below, it's a powerful illustration of how innovation, even under uncertainty, continues to push the boundaries of what humanity dares to imagine.